Welcome back to Physics 192. I'm Gerard Blanchard. Today we're going to talk about optics, specifically the way in which light waves travel. The basic idea is that light waves travel in a straight line until they encounter a surface where the index of refraction changes. And when that happens, two things can happen. The light can be reflected or it can be refracted. Take a look at this image. In this diagram, we have a beam or ray of light, which we call the incident ray, that symbolizes the direction of the initial light wave traveling towards a surface where the index of refraction changes. This could be, for example, the interface between air and a piece of glass. So the shaded region could represent a pane of glass and the unshaded region could represent the air. And we have an incident ray coming from the air. It encounters the surface of the glass and two things can happen. It can be reflected, and we represent that with the reflected ray that we've drawn in, or it can penetrate the surface and enter into the glass. And we represent that with the transmitted ray. So the basic idea here is that light waves travel in a straight line until they encounter a change in the index of refraction. And then at the surface where the index of refraction changes, we have reflection and refraction. Reflection means that the light bounces off of the surface and back into the air, and refraction means that it penetrates into the glass. The important quantity is the angle of the direction in which the light is propagating. And by convention, we're going to measure those angles with respect to the line perpendicular to the surface. So you see that we have three angles drawn in there, theta I for the angle of the incident ray, theta R for the angle of the reflected ray, and theta T for the angle of the transmitted ray. And relating these angles to one another is what this section is all about. The relationship between the incident angle and the reflected angle is very simple. The incident angle and the reflected angle are equal. So theta I equals theta R. And once again, remember that these angles are measured relative to the line perpendicular to the surface where the index of refraction changes. The transmitted ray, the angle of the transmitted ray, is related to the angle of the incident ray by an equation in I, sine theta I, or the index of refraction in the incident region times the sine of the angle that the incident ray makes with the perpendicular to the surface is equal to nt times sine of theta t. Or in other words, the index of refraction times the sine of the angle of the transmitted ray. And these two equations are the one that we're going to be using throughout this section. Theta incident equals theta reflected, and the index of refraction in the incident region times the sine of theta incident equals the index of refraction in the transmitted region times the sine of theta transmitted. Now, before we go on using those equations, I want to say a word about reflection, and specifically the distinction between what we call specular reflection and diffuse reflection. When light bounces off a very smooth surface, the light bounces in one direction, like the figure on your left. We call this specular reflection, meaning like a mirror. It reflects like a mirror. And this is the case in which we're talking about where the angle of reflection is equal to the angle of incidence. Now when light bounces off a rough surface, like the image to your right, the light bounces in all directions, and we call this diffuse reflection. Let me demonstrate that for you. Here I have a mirror. I'm going to place that on this piece of paper. And I'm going to shine a flashlight at the paper. And you can see, you can see right now that even though the paper is lit by the lights in the room, the mirror itself looks dark. And the reason for that is that the light from the lights in the room hits the paper, bounces off in all directions, and some of it bounces towards the camera. Now, the mirror, however, looks dark because there don't happen to be any lights shining so that they reflect directly into the camera. So no light is getting to the camera from the mirror. I can demonstrate that a little more using my flashlight. I'm shining a flashlight on the paper, and you can see that the flashlight is making a spot on the paper because the light, and I can even shine the flashlight over the mirror, the flashlight is making the paper brighter, but it's not making the mirror brighter. The mirror stays black. And the reason for that is that the light from the flashlight hits the paper and bounces off in all directions, and some of it goes to the camera. So it's diffuse reflection that allows us to see everything around us when it's lit up by a light. But when we're talking about a mirror, a very smooth surface, which is what we're going to be assuming for the remainder of this, section, then all of the light bounces in one direction. If I want the light from the flashlight to shine into the camera, then I have to put the flashlight in one very specific position so that the light bounces from the flashlight into the camera. And another thing that you see here is that you don't just see a glow, just a diffuse glow. What you actually see is you see the flashlight itself. You see the individual bulbs making up the flashlight. So when the light hits the paper, it bounces off in all directions. When the light hits the mirror, then you see an image of the light itself. Now, let's work some examples of the reflection and refraction of light. A light ray reflects from a plane mirror as shown in the figure. What is the angle of deviation, delta, as shown in the diagram? Go ahead and draw your own diagram. We still start everything by drawing a diagram. List your knowns and unknowns. Write down the equations that you're going to use here, and start working on that question, please. Okay, here's our diagram. Here's our incident light ray. And we're told that this is a 50-degree angle and the light bounces off. But we were asked to find the deviation from the original direction of travel of the light, and that's called delta. And so we have to draw the line perpendicular to the surface. This line is perpendicular to the surface, and this would be theta incident, and this would be theta reflected, because remember, we measure our angles for incidence and reflection and transmission relative to the perpendicular to the surface. Now, the first thing that we can see is that this is a straight line here, so theta incident plus theta reflected plus delta have to equal 180 degrees. Theta incident plus theta reflected plus delta equal 180 degrees. We also know from our equation of reflection is that theta incident is equal to theta reflection. Theta incident is equal to theta reflected. So for theta reflected, I'm just going to write theta incident. So I have theta incident plus theta incident plus delta is equal to 180 degrees, or 2 times theta incident, plus delta is equal to 180 degrees. Now what is theta incident? Well, we're told that this angle right here is 50 degrees. This is a right angle, so theta incident plus 50 must equal 90 degrees, or theta incident is 40 degrees. So we have 2 times 40 degrees plus delta is equal to 180 degrees, or 80 degrees plus delta is equal to 180 degrees, or delta is 180 degrees minus 80 degrees, and so finally delta is equal to 100 degrees. So the light is deflected from its initial path by 100 degrees. So you can see here that not only do we need to use our equations for reflection and refraction, but we're also going to have to use a lot of geometry. Let's work another example. Sunlight strikes the surface of a lake. A diver sees the sun at an angle of 42 degrees with respect to the vertical. What angle do the sun's rays in air make with the vertical? Now, to answer this, you actually need one more piece of information, and that would be the index of refraction of water, which is 1.33. So use 1.33 for the index of refraction of water. So draw your diagram and please get started answering that question. Okay, here's our diagram. Here is the surface of the water, and here is the sun, and here is our diver. Actually, let me draw some light rays here. Okay, and here is our diver. There's a sun, and here is our line perpendicular, so this is air. And the index of refraction of air, I didn't tell you, is simply 1, because light travels basically at the speed of light through air. N is exactly 1 in vacuum, but it's close enough in air that we can use N is equal to 1. And here we have water with an index of refraction of 1.33, and the light ray is incident from air and transmitted into water. So N incident is 1 and N transmitted is 1.33. This is our perpendicular line. So this would be theta incident. And that's what we're looking for. We're looking for the angle that the sun rays make with the vertical. This is our vertical line. So theta incident is what we're looking for. Down here, this would be theta transmitted, the angle that the light rays make when they're transmitted into water. And we're told that the diver sees the sun at an angle of 42 degrees with respect to the vertical. Okay, so we know the index of refraction in the incident region. We know the index of refraction in the transmitted region. We know the angle of the light rays in the transmitted region. And all we need is the angle, and what we're looking for is the angle of the light rays in the incident region. And for that, we use our equation for refraction, which is N incident times sine of theta incident is equal to N transmitted times the sine of theta transmitted, or 1 times sine of theta incident is equal to 1.33 times the sine of theta transmitted, which is 42 degrees. And 1 times sine of theta incident is just sine of theta incident. And over here, 1.33 sine of 42 degrees, 1.33 times the sine of 42 degrees is 0.890. So the sine of theta incident is 0.890. What we do now is we take the inverse sine of both sides. And the inverse sine of theta incident just gives us theta incident is equal to sine inverse of 0.890. So that tells us that theta incident is equal to inverse sine of 0.890, which is 62 degrees, or 62.9 degrees. So the angle that the sun's rays make with the vertical in air is 62.9 degrees, whereas in the water, they make an angle of 42 degrees because the light is bent or refracted upon entering the water. Let's work another example. A light ray in the core of a cylindrical optical fiber is incident on the cladding. A ray is transmitted through the cladding and into the air. The emerging ray makes an angle theta 2 equal to 5 degrees with the outside surface of the cladding. What angle, theta 1, did the ray in the core make with the axis? The index of refraction in the core is 1.4. The index of refraction in the cladding is 1.2. And the index of refraction in air is 1.00. So we're going from the axis of the core through the cladding into air. So go ahead and draw your own diagram and list your knowns and unknowns. Start using your equations and get a head start on this question, please. Okay, I'm going to start from the axis. And here we have our light ray making an angle theta 1, which is what we're looking for. That's what we're ultimately asked for. And the index of refraction here is 1.4, and this light ray encounters the cladding of the fiber. I'm going to draw that bigger than it showed in your diagram. And it is refracted in the cladding. And then it's refracted again in air. So this is what our diagram looked like. And we were told that this angle, theta 2, was equal to 5 degrees. And we were also told that the index of refraction in this area, N, is equal to 1.2. And in the air, N is equal to 1.0. Okay, so what we have here now are two surfaces. We have the light going from one region to a second region to a third region. So we have one surface here and one surface here. So what we're going to have to do is we have the light ray we have the light ray refracted at both surfaces. So we're going to have to use our refraction equation twice. Okay, what we're going to have to do is we're going to have to work backwards from air to the cladding to the core. And if this angle right here is 5 degrees, then we know that this angle here must be 85 degrees, because this is perpendicular to this boundary. This is our perpendicular to this boundary. So these two angles have to add up to 90 degrees. If this is 5, this is 85. And so we have another angle in here. We'll call that theta 3. Okay, and we're going to use our refraction equation from here to here. And so that would be N incident sine of theta incident is equal to N transmitted sine of theta transmitted. And this is for the cladding to air boundary. So as we're going from the cladding to the air. It is incident from the cladding side, so N incident is 1.2. Theta incident is theta 3, so we have sine of theta 3 here. The index of refraction in the transmitted region is 1. The angle in the transmitted region is 85 degrees, so we have the sine of 85 degrees. So what this gives me is that sine of theta 3 is equal to sine of 85 degrees divided by 1.2. I've multiplied by my 1 and I've divided by my 1.2, or theta 3 is equal to the sine inverse of sine of 85 degrees divided by 1.2. And what does that equal to? Okay, I have sine inverse of sine of 85 degrees. I'll close my parentheses and then divide by 1.2 and close my final parentheses. And so I have theta 3 is equal to 56.1 degrees. So this angle right here is 56.1 degrees. Now, since I have parallel lines, this line is parallel to this line, these two angles must be the same. So this angle in here is also 56 degrees. And here I have another angle, we'll call that theta 4. And now we're looking at refraction from the core into the cladding. So core to cladding. And once again, we have N incident, sine theta incident is equal to N transmitted, sine of theta transmitted. The light beam is incident from the core side and transmitted to the cladding. So N incident is 1.4 times sine of theta incident is equal to N transmitted, that's 1.2, times the sine of theta transmitted, which is 56 degrees. Or 56.1 degrees. I'll put that 0.1 in. And so we have sine of theta 1 is equal to 1.2 divided by 1.4 times sine of 56, and I'll put my 0.1 back in, 56.1 degrees, or theta incident is equal to the inverse sine of 1.2 divided by 1.1.4. It's 1. There we go. 1.2 divided by 1.4 times the sine of 56.1 degrees. And this is 1.2 divided by 1.4. Same as here, 1.2 divided by 1.4. Okay, so theta incident is equal to the inverse sine of 1.2 divided by 1.4 times sine of 56.1 degrees. Close my parentheses, and I have an angle of 45.4 degrees. So I have theta incident, which is actually theta 4. So theta 4 is equal to 45.4 degrees. Is that what we're looking for? Not quite. We're looking for this angle right here, but here we have a right triangle. So this angle will be 90 degrees minus theta 4. So we're looking for theta 1, which is equal to 90 degrees minus theta 4, or theta 1 is equal to 90 degrees minus 45.4 degrees. So theta 1 is going to be 44.6 degrees. Theta 1 is 44.6 degrees, so that is what we were asked for. We were asked for this angle right here, theta 1, and it is 44.6 degrees. Let's work another example. A ray of light is transmitted through a flat plate of glass as shown in the diagram, and the index of refraction of the glass is 1.52. Show that theta 3 is equal to theta 1. And for this example, use theta 1 is equal to 30 degrees, but really any angle would do. Okay, here we have our plate of glass, and it has an index of refraction of 1.52, and we have air on both sides, and the index of refraction of air is 1.00, and we have a ray of light that is incident on the glass with a theta 1 equal to 30 degrees, and it is transmitted through the glass. That's theta 2. And it goes through the glass and comes back out again. And here we have theta 3. And what we're asked to show is that theta 3 is the same as theta 1. Okay, well, let's start going from air into glass. In incident, sine of theta incident is equal to in transmitted, sine of theta transmitted, and this is air to glass. So in incident is 1 times the sine of 30 degrees is equal to in transmitted, that would be 1.52, times the sine of theta transmitted, so that would be the sine of theta 2. So the sine of 30 degrees divided by 1.52 is equal to the sine of theta 2, or the inverse sine of 30 degrees divided by 1.52 is equal to theta 2. So what is theta 2 equal to? We have the inverse sine of the sine of 30 degrees divided by 1.52. And that tells us that theta 2 is equal to 19.2 degrees. So this angle is 19.2 degrees. Well, once again, these two sheets of the two sides of the plate of glass are parallel to each other. So their perpendicular lines are parallel to one another. So this is parallel to this. That means that this angle is the same as this angle. So this angle in here is 19.2 degrees. And so now we can do our refraction equation at the glass to air boundary. So glass to air, we have in incident, sine of theta incident is equal to in transmitted, sine of theta transmitted. Now we're incident from the glass side, so this would be 1.52 times the sine of theta incident, 19.2 degrees, is equal to in transmitted, which is air, so it's 1 times the sine of theta transmitted, and that is theta 3 times the sine of theta 3. So the inverse sine of 1.52 times the sine of 19.2 degrees is equal to theta 3. And so what is theta 3 equal to? The inverse sine of 1.52 times the sine of 19.2 degrees gives us 30 30.0 degrees. So this angle, theta 3, is also 30 degrees. So if this is 30 degrees, this is 30 degrees, really whatever theta 1 is, theta 3 will be the same. And the reason why that is because these two surfaces here and here are parallel to one another. And if these two surfaces are parallel to one another, then these normals will also be parallel to one another, and these two angles will be the same. That's why that works. So, when this side of the glass and this side of the glass are parallel to one another, this angle and this angle will be the same. Let's work an example next where that is not the case, where this side and this side are not parallel to one another. The prism in the figure is made of crown glass. The index of refraction is 1.52. Find the angle with respect to the original ray for the light transmitted into air through the right side of the prism. Now go ahead and draw your diagram and start listing your knowns and unknowns and get a head start on this question. Okay, here is our prism. This is 60 degrees here. We have a light ray that makes an angle of 55 degrees with respect to the perpendicular of this side that is transmitted through the prism. And we have an angle theta 2. It's transmitted across. It encounters this side, and it is refracted. So let's call this theta 3, and I'll call this theta 4. Okay. And this is glass with an index of refraction of 1.52. And this is air with an index of refraction of 1.00. And at all of our boundaries, remember that our equation is N incident sine theta incident is equal to N transmitted sine of theta transmitted. I'm not going to write that down in that form each time. Okay, so let's figure out theta 2 to begin with at the air to glass interface. And we have in incident, which is 1, the index of refraction in air, 1 times the sine of theta incident, which is 55 degrees, is equal to N transmitted, 1.52, times the sine of theta transmitted, which is theta 2. So this tells us that sine of 55 degrees divided by 1.52 is equal to sine of theta 2, or the sine inverse of the sine of 55 degrees divided by 1.52 is equal to theta 2. And so theta 2 is equal to sine inverse of the sine of 55 degrees divided by 1.52. Theta 2 is 32.6 degrees. So theta 2 is 32.6 degrees. Okay. Now we need to figure out theta 3 right here so that we can do the glass to air interface. Well, we're going to have to do that using this triangle right here. Note that this is a right angle right here. This is a right angle. So this angle, I'll draw it in with 2 lines. I'll call that, well, actually I don't have to even give it a name, but this angle is going to be 90 degrees minus 32.6, and so that's going to be 57.4 degrees. Because 32.6 plus 57.4 is going to give us 90 degrees. So now I have this angle right here, this angle right here. This angle is going to be 180 degrees minus these 2 angles, because the sum of the angles in a triangle have to be 180 degrees. So this angle right here, I'll call that theta 3. We know that theta 3 is equal to 180 degrees minus 60 degrees minus 57.4 degrees. Or theta 3 is equal to 180 degrees minus 60 degrees minus 57.4 degrees, and that would be 62.6 degrees. Oops, actually I can't call that theta 3. I've already used theta 3. Well, actually I'll call this one, theta 5 then, because this has to be different than that angle right there. But I know that theta 3 and theta 5 have to also add up to 90 degrees, since this is a right angle in here. So theta 3 and theta 5 have to equal 90 degrees. So theta 5 is 90 minus 62.6. 90 minus 62.6. And that would be 27.4. So theta 5 is 27.4 degrees. So now we have the incident angle at this glass to air interface. So the angle between the light ray and the perpendicular to the surface right here is 27.4 degrees. So we'll use our equation again, glass to air. Okay. And in the glass, we have index of refraction of 1.52 times the sine of this angle in here, 27.4 degrees. And that's equal to the index of refraction in air, which is 1, times the sine of theta 4. So sine inverse of 1.52 times sine of 27.4 is equal to theta 4. And so what is that? Sine inverse of 1.52 times the sine of 27.4 is 44.4 degrees. Is theta 4. Okay, so what we see is that this light has been bent as it passed through, has been bent overall. It was moving up to begin with. Now it's moving down. So the light ray from moving from its original direction has been bent overall in the direction towards the thicker part of the prism. Now we haven't actually answered the question that was asked yet, because we were asked for the deflection relative to the direction of the original ray. So we're going to have to do one more thing. We're going to have to carry the original ray through the glass, carry the original ray all the way through the glass, and find out what angle it makes with respect to the perpendicular. Okay, so we know that this light ray makes an angle of 44 degrees with respect to the perpendicular. What angle did this light ray make with respect to the perpendicular on this side? Okay, if this angle right here is 55 degrees, then we know that this angle over here is going to be 90 minus 55, or this is going to be 35 degrees. So we have a 55 degree angle here, a 35 degree angle here, which means that this angle over here is also 35 degrees. If this angle is 35 degrees, this angle is 60 degrees, then the angle over here is going to be 180 minus 60 minus 35. 180 minus 60 minus 35. This is going to be an 85 degree angle. And that leaves us with this angle in here, which is going to be 90 degrees minus 85, or 5 degrees. And so we see that if the original light ray had passed without any refraction through the prism, it would have come out on this side, making an angle of 5 degrees with respect to the perpendicular, whereas now, since it has been refracted, it's making an angle of 44 degrees with respect to the perpendicular on this side. So the total deflection, delta, is 44.4 degrees minus this 5 degrees right here. So delta is 39.4 degrees. So overall, the overall effect of this prism is to bend the light by an angle of 39.4 degrees towards the thicker end, or the base of the prism. This is going to be very important when we come back next time and talk about lenses. Until then, think physics.